November 23, 1942. Alamein, Egypt. A captured Willys MB sits on wooden trestles in an Afrika Korps field workshop. The hood latch releases with a simple twist. Spark plugs emerge from their wells, showing minimal carbon buildup despite hard use. The transfer case lever moves smoothly through its positions, revealing selectable four-wheel drive. German mechanics circle the vehicle with professional curiosity, mixed with skepticism bred from months fighting Allied forces. They expect fragile American mass production, improvised engineering disguised as military equipment. What they discover over the next 4 hours will challenge every assumption Berlin has taught them about industrial warfare. The frame rails measure thicker than German standards require. Every component sits within easy reach for field repair. Most troubling, this 2,450-pound vehicle mounts capabilities German light vehicles completely lack. Behind these mechanics, production statistics they cannot yet know tell the real story. Germany has built roughly 15,000 Kübelwagens by late 1942. America has already delivered over 200,000 Jeeps and will reach 640,000 by war's end. The story behind that captured Jeep begins not in a desert repair bay, but at drawing boards separated by an ocean and by fundamentally different philosophies about what military vehicles should be. August 10, 1941. Wolfsburg, Germany. Production supervisor Heinz Nordhoff sits at his desk reviewing weekly output figures for the Kübelwagen Type 82. The ledger shows 312 units completed during the previous 7 days, bringing the monthly total to approximately 1,250 vehicles. A staff officer from Panzergruppe Afrika stands beside him, reviewing a logistics memo requesting additional light reconnaissance vehicles for desert operations. The numbers do not match requirements. Dr. Ferdinand Porsche's design bureau has delivered precisely what Wehrmacht specifications requested. An air-cooled flat-4 engine displacing 985 cubic centimeters produces between 23.5 and 25 horsepower at 3,300 revolutions per minute. The engine weighs approximately 290 pounds, complete with all accessories. Swing axle independent suspension using transverse torsion bars provides adequate ride quality while minimizing parts count. The vehicle's empty weight reaches approximately 1,500 pounds. Berlin's propaganda films showcase it as the ideal soldier's companion, nimble across varied terrain. Reality diverges from promotional material in ways that matter under combat conditions. The rear-wheel drive configuration concentrates power on just 2 wheels. In soft sand, those wheels dig rather than grip. Ground pressure from narrow 5.25-inch tires proves inadequate for loose surfaces. The 23.5 horsepower output restricts maximum payload to roughly 800 pounds. Gradeability tops out at approximately 25 degrees on firm surfaces, less on loose ground. Wehrmacht field reports from North Africa document problems accumulating. Units describe Kübelwagens immobilized in sand, requiring push assistance from multiple soldiers. Recovery operations consume hours that could support combat operations. A memo dated July 19, 1942, from Oberkommando der Wehrmacht acknowledges that cross-country light transport requirements exceed available inventory by approximately 40%. The gap widens monthly as operational demands accelerate faster than production can supply. By mid-1942, fewer than 15,000 Kübelwagens have reached frontline units across all theaters. Demand continues accelerating while German armaments planners face impossible allocation decisions. Limited steel, rubber, and manufacturing capacity must serve competing requirements for tanks, aircraft, artillery, trucks, and light vehicles. The Kübelwagen represents rational engineering for a nation expecting brief campaigns. Extended war exposes limitations that doctrine never anticipated. While German engineers wrestled with resource constraints, Their American counterparts pursued a different approach entirely. The philosophy shaping American military vehicles had more in common with Detroit assembly lines than traditional military arsenals. Washington, District of Columbia. The munitions building houses U.S. Army Quartermaster Corps headquarters. In mid-July 1941, procurement officers review contracts requiring signatures. Colonel William F. Lee picks up his pen and signs standardized production agreements with Willys Overland Motors in Toledo, Ohio, and Ford Motor Company. The contracts specify unprecedented requirements that will reshape American military logistics. Every component must interchange between manufacturers without modification or fitting. Willys will produce the MB variant. Ford will manufacture the GPW variant. The only significant difference will be stamped F markings on Ford-produced components. A mechanic in North Africa must be able to install a Ford transmission into a Willys vehicle using standard tools within 30 minutes. No filing, no adjustment, no custom fitting. The specifications demand coordination that challenges normal competitive practices. Joint engineering meetings establish master drawings both companies must follow precisely. Tolerance specifications tighten beyond normal automotive practice. A bolt hole must measure 0.3125 inches plus or minus 0.002 inches, whether drilled in Toledo or Dearborn. Gauge inspection procedures standardize across facilities. Parts passing inspection at one plant must fit assemblies at the other without question. The Quartermaster Corps insists on this standardization despite manufacturer protests about increased costs and complexity. Military planners understand logistics efficiency gained through interchangeability outweighs production challenges. Technical Manual 9-803 will eventually codify maintenance procedures in 218 pages of detailed instructions, creating standardized training that allows any mechanic to service any Jeep, regardless of origin. The vehicle design itself reflects American industrial philosophy rather than military tradition. A 2,199 cubic centimeter L-head four-cylinder engine produces approximately 60 horsepower at 4,000 revolutions per minute. The cast iron block and head use conventional water cooling, a Warner Gear T84 3-speed transmission with synchronized second and third gears connects to a Spicer Model 18 2-speed transfer case. This transfer case allows drivers to select two-wheel drive for roads or four-wheel drive for terrain. An additional low-range reduction provides 1.97 to 1 gearing for maximum traction. Dana Spicer axles front and rear use 4.88 to 1 ring and pinion gears, distributing power to all four wheels when engaged. Semi-elliptic leaf springs provide suspension, simpler than torsion bars, but easier to repair using basic blacksmithing equipment at forward workshops. Combat-loaded weight reaches 2,450 pounds. This represents 950 pounds more than the Kübelwagen, but greater power and four-wheel drive capability compensate for the penalty. Where German designers optimized for lightness and efficiency, American engineers prioritized capability and field serviceability. These contrasting philosophies produced vehicles reflecting the nations that created them. The Kübelwagen embodied elegant economy, doing more with less through careful engineering. The Jeep represented industrial abundance, solving problems through robust over-engineering and standardized mass production. Neither approach was inherently superior in abstract terms, but the Desert War would soon reveal which philosophy better suited prolonged industrial conflict. The operational implications of these design choices emerged gradually through the grinding attrition of desert warfare. British 8th Army maintained detailed vehicle status boards at forward command posts. Columns tracked availability across 3 categories: operational, repair, non-operational. Workshop officers updated these boards hourly as maintenance reports arrived from scattered units operating across hundreds of square kilometers. American Jeeps under Lend-Lease allocation showed different patterns than British or German vehicles. When a Jeep required a water pump replacement, the part typically arrived within 48 hours from standardized supply stocks managed through systematic inventory control. The mechanic removed 6 bolts, extracted the failed pump, installed the replacement, torqued the bolts to specification, refilled the cooling system, and returned the vehicle to operational status. Total time: approximately 30 minutes plus cooling system bleeding. When a Kübelwagen needed a specialized component, requests moved through German logistics chains already strained by distance and Allied interdiction. The part might arrive in days, weeks, or not at all. Workshops compensated through improvisation and repair of components that American mechanics would discard. A German mechanic, facing a failed water pump, disassembled it completely, inspected components, replaced bearings if available, lapped sealing surfaces, reassembled carefully, tested thoroughly. Total time: 3 to 6 hours, assuming parts availability. 8th Army maintenance summaries compiled monthly documented the differential clearly. American vehicle repair turnaround times averaged hours for routine service. German vehicle repairs averaged days. The mathematics compounded over weeks and months into measurable operational advantage. British armored reconnaissance units operating American Jeeps accumulated more usable miles weekly than comparable German formations using Kübelwagens. This wasn't dramatic in any single instance, but the cumulative effect reshaped what commanders could attempt tactically. German logistics faced different constraints that progressively worsened as the campaign continued. Axis convoy records documented approximately 30% fuel losses on the Tripoli to front route through combination of Allied air interdiction and unavoidable wastage during transport. Every leader must travel over 1,000 kilometers through hostile airspace across terrain offering minimal cover. German units rationed movement carefully, planning operations around available fuel stocks rather than tactical opportunity alone. The mathematics of supply determined what commanders could attempt regardless of tactical skill or unit capability. These operational realities set the stage for the encounter that would prove decisive. When British forces delivered that intact Willys MB to a German workshop in November 1942, they provided more than a captured vehicle. They delivered a comprehensive education in industrial warfare that German observers were uniquely positioned to understand. The captured Jeep arrived at the workshop compound shortly after dawn. British recovery crews had towed it from the battlefield the previous afternoon, following a confused engagement where American crews abandoned vehicles during rapid withdrawal. The Jeep showed minor battle damage. Several bullet holes perforated the body panels. The windscreen had cracked, but mechanically it appeared sound, and that made it perfect for detailed examination. Oberfeldwebel Karl Fischer, senior mechanic of this Afrika Korps repair detachment, approached the vehicle with professional interest. He had examined captured British equipment before. This represented his first opportunity to inspect American light vehicles in detail. Standing orders required technical evaluation of all captured enemy equipment to assess capabilities and identify vulnerabilities. Fischer organized his team methodically, understanding that this examination could provide intelligence valuable far beyond their repair compound. They began with external inspection documenting dimensions and features. Overall length measured 132 inches from front bumper to rear. Width spanned 62 inches. Height to windscreen top reached 72 inches with canvas top erected. Ground clearance beneath the differential housing measured 8.75 inches. Wheelbase spanned 80 inches. Track width front and rear measured 49 inches identically. The tires, 6x16 Goodyear military specification, showed aggressive tread patterns designed for multiple surface types. Fischer noted tire pressure specifications stamped on a data plate mounted on the dashboard. Highway operation, 35 pounds per square inch. Cross country, 20 pounds per square inch. Sand, 15 pounds per square inch. This attention to operational flexibility impressed him immediately. German vehicles typically specified a single pressure for all conditions. The Americans had engineered adjustability into their doctrine, recognizing that proper inflation significantly affected traction and mobility across different terrain. It was a small detail that revealed larger thinking about how vehicles would actually be used in field conditions. External features revealed design priorities throughout. The hood comprised 9 separate panels secured by simple spring catches, requiring no tools for removal. Fisher timed the process. Complete engine access required 1 minute 40 seconds. The grille consisted of 11 vertical slats, stamped steel painted olive drab. The front bumper mounted extensions serving multiple purposes: jacking points, towing shackles, tool mounts. 2 jerrycans bracketed the rear body secured by quick-release straps. A shovel mounted on the left side, an axe on the right, both accessible without removing cargo. Everything suggested designers who understood that vehicles operate in field conditions far from factory support. The mechanics began disassembly following systematic procedures. Fisher photographed each stage using a Leica camera requisitioned from quartermaster stores. The technical report would require documentation. Each photograph must show clear detail for analysis by engineers in Germany who would never see the vehicle itself. The film was precious. Fisher limited himself to 47 exposures across 4 hours of examination, choosing each shot carefully to capture maximum information. Hood panels lifted away, revealing the engine compartment in all its accessible glory. The L-head 4-cylinder engine sat openly accessible without the tight packaging that characterized German designs. The spark plugs mounted vertically in the cylinder head, requiring only a deep socket for removal. Fisher extracted one, examined it carefully. The electrode showed normal wear, minimal carbon deposits, despite hard use. The gap measured correct at 0.03 inches, checked with a feeler gauge. American quality control appeared consistent, even in components manufactured for hard use and eventual disposal. The carburetor, a Carter Model W0539S, sat prominently accessible for adjustment or replacement. The distributor mounted at the front of the engine, requiring only 3 bolts for removal. The water pump, generator, and fan assembly could all be replaced as complete units without disturbing other systems. Fisher noted this repeatedly in his examination notes. German vehicles often required removing or loosening multiple components to access a single failed part. This American design philosophy prioritized field maintenance over manufacturing convenience, accepting complexity in initial assembly to simplify later service. What impressed Fisher most was discovering this wasn't accident or afterthought. Every major component showed evidence of deliberate design for field service. The oil filter mounted externally, where it could be changed without crawling under the vehicle. The fuel pump sat alongside the engine, accessible from above. The battery resided in a tray that lifted out completely for service or replacement. Belts could be checked and adjusted without special tools. The entire design reflected systematic thinking about maintenance requirements under combat conditions. The transfer case proved particularly interesting to Fisher and his team. They had heard reports about American four-wheel drive vehicles, but this represented their first hands-on examination of the mechanism. The Spicer Model 18 used elegantly simple design that impressed German engineers familiar with more complex attempts. A planetary gear set provided high and low range selection. A dog clutch engaged front axle drive. Total major components: approximately 40 pieces plus bearings and seals. The mechanism could be disassembled completely, using basic tools available in any field workshop. Fisher compared this mentally to German four-wheel drive attempts he had encountered. The Volkswagen Schwimmwagen amphibious vehicle employed more complex mechanisms, requiring more parts and more precise assembly. The American approach sacrificed some theoretical efficiency for robustness and serviceability. The design tolerated wear and imperfect adjustment while maintaining function. A mechanic with moderate skill could rebuild this transfer case in field conditions without specialized training or tools beyond those carried in standard workshop kits. Frame construction showed characteristics that seemed wasteful by German standards until viewed through the lens of battlefield durability. The rails measured 3 over 16-inch thick, approximately 4.8 millimeters. German practice typically employed 3 millimeters for comparable applications. This extra material added roughly 60 pounds to the vehicle's empty weight. But Fisher noted several bullet strikes on the frame that had penetrated the metal but not caused structural failure. A thinner frame might have cracked completely under the same impact, rendering the vehicle irreparable in field conditions. The Americans had engineered in a safety margin that cost weight but provided survivability. The front axle used open-knuckle ball joints, allowing approximately 25 degrees of steering angle. Both front and rear axles featured semi-floating design, with tapered roller bearings supporting the axle shafts. The suspension employed 9-leaf springs front, 11-leaf springs rear. Everything appeared straightforward to service. Spring replacement required no specialized equipment beyond basic hand tools and a jack. A damaged spring could be replaced in perhaps an hour under field conditions, returning the vehicle to service quickly. By midday, Fisher's team had removed and examined nearly every major component accessible without complete disassembly. They had measured critical dimensions with precision instruments. They had photographed key features from multiple angles. They had tested systems repeatedly to understand operational characteristics. The accumulated evidence challenged comfortable assumptions about American engineering capabilities that German propaganda had fostered. This vehicle demonstrated sophisticated design philosophy. Disguised as simple execution, every component appeared optimized for field service, rather than manufacturing convenience or theoretical efficiency. The engine accessible through simple hood removal, the transfer case rebuildable with basic tools, the suspension serviceable using blacksmith equipment available at any forward workshop. The electrical system standardized throughout, using common bulb types and fuse ratings. The fuel system straightforward, with gravity feed from tank to mechanical pump. Everything suggested designers who understood that vehicles operate in field conditions far from factory support, often under enemy fire, maintained by mechanics with varying skill levels, using whatever tools were available. Most significantly, examination of manufacturer markings revealed standardization between companies that exceeded anything in German experience. Some components bore Willys Overland markings clearly stamped into castings or forgings. Others showed Ford identification codes. Yet everything fit together precisely without adjustment or modification. The clutch assembly came from Ford. The transmission showed Willys markings. The transfer case bore no manufacturer marking, suggesting common supplier to both companies. The axles carried Dana Spicer identification. Every piece worked together as if manufactured in a single facility to uniform standards. Fisher understood immediately what this meant for American logistics. German supplier networks required manual fitting to accommodate tolerance variations between component sources. Skilled workers spent hours adjusting parts to ensure proper fit during assembly. This craft approach ensured quality but fundamentally limited production rates and complicated field maintenance. The Americans had achieved true interchangeability through manufacturing discipline Germany had not matched, despite decades of industrial development. This wasn't superior resources or bigger factories. This was superior industrial organization applied systematically. Fisher completed his preliminary report that evening under kerosene lamplight. 23 typed pages, with 47 photographs and 12 technical drawings created by the detachment's draftsman. The report described Jeep characteristics with professional objectivity, avoiding emotional language or propaganda-style dismissal of enemy capabilities. The vehicle demonstrated remarkable simplicity of design that paradoxically required sophisticated manufacturing to achieve. Components showed excellent accessibility for maintenance. The four-wheel drive system with selectable engagement provided capabilities German light vehicles lacked entirely. The report included recommendation for pursuing similar four-wheel drive development for German light vehicles, noting that such capability would significantly improve cross-country performance. But Fisher included sober assessment that would prove prophetic. Available production capacity cannot accommodate such programs given existing priorities and resource constraints. The German automotive industry was already stretched to breaking point. Adding four-wheel drive systems to light vehicles would require retooling, new supplier development, additional materials, and manufacturing capacity that simply did not exist. Germany recognized the capability but lacked means to replicate it. The recommendation represented professional acknowledgement of enemy capabilities rather than practical proposal for German response. What Fisher could not know was that this single vehicle examination represented only the visible tip of a production disparity that would ultimately prove decisive. The numbers behind that captured Jeep told a story that no amount of tactical excellence could overcome. German armaments officials were already beginning to grasp the scale of the problem, though the full magnitude would not become clear for months. Production analysts in Berlin reviewed comparative charts showing output figures that seemed impossible, yet proved accurate upon verification through multiple intelligence sources. Volkswagen's monthly output averaged approximately 1,500 Kübelwagens during the final quarter of 1942. This represented significant achievement requiring coordination of approximately 250 suppliers, providing components ranging from engines to body panels to electrical systems. Each supplier faced its own constraints regarding materials, labor, machine tools, and electricity. Production planners balanced competing demands across an economy already stretched by total war mobilization affecting every industrial sector. Combined American production from Willys and Ford exceeded 10,000 Jeeps monthly during peak periods in late 1942 and early 1943. Willys averaged approximately 6,500 units from their purpose-built Toledo facility. Ford added roughly 4,000 from their Richmond, California plant, while simultaneously producing other military vehicles. This represented nearly 7 times German output from just 2 manufacturers, and the disparity was widening rather than narrowing. As American production continued ramping up, while German output stagnated under accumulating constraints. The Willys Toledo plant employed approximately 14,000 workers across 3 shifts operating 24 hours daily. The facility had been purpose-built for Jeep production during 1941, designed specifically for volume manufacturing using automotive industry methods perfected over decades of civilian production. The main assembly line moved at carefully calculated pace, approximately 3.8 minutes per station. Workers performed specific tasks as vehicles passed their positions. Station 1 received bare frame assemblies from the frame shop, where welding operations joined stamped steel rails into rigid structures. Station 3 installed front spring assemblies using air-powered impact wrenches torqued to specification, eliminating variability from human judgment. Station 7 mounted the rear springs following identical procedures. Station 14 received the engine transmission assembly, pre-mounted on a subframe in a separate production area. Workers bolted this complete powertrain to the main frame, using standardized bolt patterns that allowed no ambiguity about proper positioning. Station 18 connected steering linkage, a 4-minute task requiring 3 workers coordinating their efforts. Station 23 installed the transfer case and connected drive shafts arriving from dedicated production lines. Station 27 mounted front and rear axle assemblies that had been built, filled with lubricant, and tested in yet another separate operation. The process continued through 73 stations until complete vehicles drove off the line under their own power. Each vehicle received final inspection checking approximately 150 individual points before acceptance for military delivery. Vehicles failing inspection returned for correction rather than being accepted with defects. Systematic quality control caught problems before vehicles reached units where failures would compromise operations. The entire system reflected manufacturing philosophy, prioritizing reproducibility and consistency over individual craftsmanship or artisan skill. Ford's operation at Richmond, California, followed similar organization adapted from automobile production experience accumulated over 4 decades. Ford employed approximately 12,000 workers, building GPW Jeeps alongside other military vehicles in facilities that had manufactured civilian vehicles until conversion to war production. The company's experience mass-producing Model T and Model A automobiles translated directly to military applications. Henry Ford's lifelong obsession with production efficiency manifested in assembly line timing studies measuring every motion workers performed, seeking to eliminate wasted effort and optimize workflow. Workers received training in specific task sequences designed to minimize unnecessary movement. Parts arrived at stations in containers positioned for optimal reach, eliminating time spent searching or sorting. The facility achieved production of approximately 135 Jeeps daily at peak output. This rate seemed impossible to German observers reviewing captured production statistics and intelligence reports. One American factory complex was outproducing Germany's entire light vehicle industry by factors that defied comprehension based on traditional manufacturing assumptions. But numbers alone did not tell the complete story. The production differential reflected multiple compound factors beyond simple facility size. American plants operated with consistent electrical power, rarely interrupted even during storms. German facilities experienced frequent power disruptions from Allied bombing of electrical generation and distribution infrastructure. American plants possessed adequate machine tool inventory maintained properly. German machine tools were aging, overworked, and increasingly difficult to repair as strategic materials became scarce. American plants received reliable supplier deliveries on predictable schedules. German suppliers faced transportation disruptions from bombing and fuel shortages, causing unpredictable delays. Most significantly, American facilities employed large pools of adequately trained workers who received systematic instruction in specific tasks. German facilities suffered progressive replacement of skilled workers drafted into military service with forced laborers possessing minimal training and no motivation beyond avoiding punishment. The quality of German production declined measurably as the war progressed, while American production maintained consistent standards through systematic processes that did not depend on individual worker skill or dedication. Albert Speer's armaments production reports documented German efforts to increase output through rationalization and better resource allocation. Achievements proved substantial by any reasonable measure. German production increased significantly under Speer's direction compared to pre-1942 methods. Manufacturing efficiency improved through centralized planning and elimination of redundant operations. Standardization increased where possible within resource constraints, but absolute numbers remained constrained by factors beyond organizational improvement or administrative efficiency. Allied strategic bombing progressively degraded German manufacturing capacity faster than improvements could compensate. Raw material shortages limited what could be produced regardless of factory efficiency or worker productivity. Transportation network damage restricted movement of components between facilities, turning just-in-time delivery into unpredictable chaos. The comparison with American production grew more lopsided over time, rather than narrowing despite German efforts, demonstrating that organizational improvements cannot overcome fundamental resource disadvantages and physical destruction. These production statistics mattered because they translated directly into operational capabilities that shaped what was possible tactically. The numbers weren't abstract. They represented vehicles either available or absent when units needed them for missions that would succeed or fail based on mobility, and logistics. British technical evaluation teams conducted systematic testing that quantified capability differences which field experience had suggested. A measured test course outside Tripoli allowed controlled comparisons between captured German vehicles and Allied equipment under identical conditions. The testing revealed gaps that exceeded expectations. The Kübelwagen demonstrated superior fuel economy on firm surfaces, a predictable advantage from air cooling and lighter weight. Running at steady 30 miles per hour on improved roads, it achieved approximately 30 miles per gallon. For extended road operations, the German vehicle showed clear efficiency advantages that mattered when fuel supplies were constrained. But the soft sand test revealed fundamental limitations that no amount of driver skill could overcome. The Kübelwagen's rear-wheel drive concentrated power on just 2 wheels. In loose sand, those wheels dug trenches rather than propelling the vehicle forward. The driver attempted various techniques learned through field experience. Building momentum on firm ground failed after approximately 30 meters when the vehicle bogged completely. Reducing tire pressure to 10 pounds per square inch improved flotation slightly, but proved insufficient for sustained progress. The test team recorded vehicle immobilized in soft sand, requiring external assistance in their evaluation report, a clinical description of tactical limitation. The Jeep tackled the same 800-meter loop in 4-wheel drive low range. All 4 wheels distributed power-spreading vehicle weight across doubled contact patches. When one wheel encountered soft spots, the other 3 maintained forward progress. The Jeep completed the entire circuit without stopping. The driver reported the vehicle felt controllable throughout, despite challenging surface conditions that would defeat 2-wheel drive vehicles regardless of power or weight. This wasn't marginal advantage. This was categorical difference in capability. Gradeability testing quantified performance differential with precision that confirmed field observations. The Kübelwagen managed approximately 23 degrees maximum grade on firm surfaces. Above that angle, the rear wheels lost traction despite weight transfer rearward during climbing. The engine's modest 23.5 horsepower output proved insufficient for steeper angles, even on surfaces providing good traction. Tactical reconnaissance requiring movement into hilly terrain faced real limitations. The Jeep, engaging 4-wheel drive low range, climbed the 35-degree test grade successfully on the first attempt. The combination of 60 horsepower, low-range gearing providing mechanical advantage, and 4-wheel traction enabled the vehicle to pull itself up slopes that would defeat the Kübelwagen. The test team ran the evaluation 3 times with identical results. The capability gap was not marginal or dependent on driver technique. It was fundamental, inherent in the design choices each nation's engineers had made. Drawbar pull measurements quantified towing capacity differences that affected mission capabilities directly. The test team used a spring scale measuring force required to move a standardized anti-tank gun on level firm ground. The Kübelwagen generated approximately 1,200 pounds of pulling force before rear wheel slip occurred. This proved adequate for light loads on good surfaces, but insufficient for heavier equipment or difficult terrain that units commonly encountered. The Jeep produced approximately 2,500 pounds of pulling force in low-range 4-wheel drive before any wheel exhibited slip on the same test surface. This represented more than double the German vehicle's capability, a difference that mattered practically. A Jeep could extract a bogged truck using its own traction, where a Kübelwagen would require additional vehicles or manpower. A Jeep could tow artillery pieces that would require multiple Kübelwagens working together, tying up scarce vehicles for single tasks. Combat support missions benefited directly from superior capability that came standard rather than requiring special equipment. German technical observers attending these tests documented findings carefully in reports forwarded through intelligence channels. The conclusions were professional and objective, avoiding propaganda-style dismissal while honestly assessing capability gaps. The four-wheel drive system, with low-range gearing, provided capabilities fundamentally unmatched by rear-drive configuration, regardless of how well that simpler system was engineered. The performance gaps appeared largest precisely in conditions where light vehicles operated most frequently: soft terrain, steep grades, heavy towing loads. These findings circulated through German technical intelligence services with clear implications. American light vehicles demonstrated superior operational capabilities in cross-country conditions despite higher fuel consumption and greater mechanical complexity. The trade-offs American designers accepted: additional weight, more complex drivetrain, higher fuel consumption, proved worthwhile in field operations, where capability mattered more than theoretical efficiency. German after-action reports from multiple theaters increasingly noted that Allied mobility advantages extended beyond simple numbers to superior capability per vehicle, multiplying the numerical disadvantage. But test course evaluations only confirmed what German soldiers already knew from direct combat experience. The real education came from sustained exposure to American methods and equipment, under conditions that allowed careful observation. When Axis forces in Tunisia finally surrendered in May 1943 after months of fighting that progressively isolated German and Italian units from supply sources, approximately 275,000 prisoners entered Allied custody. Among them, roughly 130,000 Germans represented units from across Rommel's Afrika Korps. The prisoner stream included several hundred German mechanics possessing specialized technical knowledge that Allied intelligence found valuable. Interrogation teams worked systematically, seeking information about German equipment, tactics, logistics, and industrial capacity. German mechanics received particular attention. What did they know about Allied equipment encountered during the campaign? What impressed them? What disappointed them? The answers revealed patterns that intelligence analysts compiled into summary reports. The prisoners described American logistical abundance consistently across hundreds of independent interrogations conducted by different teams in separate facilities. They mentioned seeing supply dumps containing more material than entire German divisions possessed. One Unteroffizier, captured with Panzer Regiment 5, described examining an American supply dump in detail. He estimated the dump contained food sufficient for 20,000 men for 30 days. Fuel stocks appeared to exceed 1 million liters. Ammunition crates, stacked in organized rows, stretched across several hundred meters. Spare parts filled multiple tents. The quantities seemed impossible based on his experience with German logistics struggling to deliver basic requirements across similar distances. They recalled American vehicles being abandoned after minor mechanical problems because unit policies favored requisitioning replacements rather than conducting field repairs. This seemed wasteful to Germans, accustomed to coaxing maximum service from limited equipment, but reflected different resource positions. They described maintenance practices emphasizing component replacement rather than repair, with worn parts discarded that German workshops would carefully rebuild over hours of skilled labor. Most significantly for American intelligence analysts compiling these reports, prisoners referenced parts interchangeability between American vehicles as something remarkable and absent from German logistics systems. A Feldwebel mechanic from a workshop company explained that German practice assumed parts must be matched to specific vehicles or at minimum to specific production batches. Components from different suppliers rarely interchanged without fitting and adjustment by skilled workers. American vehicles apparently achieved true interchangeability, where any part bearing correct part number fit any vehicle regardless of source, date, or manufacturer. The contrast reflected different resource positions and industrial philosophies that prisoners described without fully understanding the strategic implications. German workshops repaired components because replacement parts arrived slowly, if at all, through logistics chains stretched across thousands of kilometers under constant Allied interdiction. Mechanics invested hours rebuilding water pumps, generators, starters, and other components that American units simply replaced from stockpiled spares. A German mechanic might spend 6 hours rebuilding a water pump to save a component costing perhaps 50 Reichsmarks. An American mechanic installed a new pump in 30 minutes because parts abundance made repair economically senseless compared to labor cost and vehicle downtime. Neither approach was inherently superior in abstract theoretical terms divorced from context, but operational outcomes favored shorter downtime and higher vehicle availability rates in real-world conditions. German units maintaining 70% vehicle availability through intensive repair work still operated at disadvantage against American units, maintaining 90% availability through rapid parts replacement. The cumulative effect across thousands of vehicles created measurable operational advantages that shaped what was possible tactically. Allied intelligence compiled these prisoner accounts into summary reports distributed through military planning channels. The interrogation data confirmed earlier assessments based on captured documents and equipment examination. American industrial capacity provided material advantages exceeding simple numerical superiority. The logistics system supporting Allied operations functioned more efficiently through standardization and parts abundance than German logistics struggling with resource constraints and component scarcity. But the most profound education in American industrial methods came not from brief interrogations in the aftermath of capture, but from sustained exposure over months of daily work. German prisoners assigned to labor details at American facilities observed American maintenance operations from inside the system rather than as enemies examining captured equipment or defeated soldiers answering questions. This sustained exposure provided insights that would prove surprisingly relevant decades later. Camp Hearn, Texas, occupied 705 acres of former farmland in Robertson County, northeast of Houston. Established during 1943 using standard military designs, the camp confined approximately 5,000 German prisoners in 6 compounds, containing 625 white-painted frame buildings. Guard towers stood at compound corners. Double barbed wire fences surrounded the perimeter. Interior wire separated compounds housing officers from enlisted prisoners. Despite security measures, conditions proved relatively comfortable by prisoner of war standards. Barracks provided individual beds. Heating functioned in winter. Cooling fans offered relief during brutal summer heat. Mess halls served food meeting convention standards. Recreation facilities included sports fields, a library, and craft workshops. Among Camp Hearn prisoners, approximately 400 possessed mechanical and technical skills documented in German military records. Automotive mechanics, aircraft mechanics, ship engineers, industrial machinists, tool and die makers, electricians, welders. American authorities assigned German mechanics to work details at the camp motor pool and nearby military maintenance facilities. The prisoners worked under supervision, performing routine service, diagnosing problems, replacing components, conducting inspections, maintaining records. Each prisoner received small payment, credited to accounts managed by camp authorities. More significantly, the work provided relief from camp boredom, an opportunity to exercise professional skills. What German mechanics observed during months of sustained work provided education in American industrial methods, proving more valuable than any single technical specification or captured equipment examination could offer. The motor pool at Camp Hearn maintained approximately 250 vehicles of various types: trucks, jeeps, staff cars, ambulances, wreckers, tractors, trailers. The facility operated with standardization that German prisoners found initially puzzling, then increasingly impressive, as they understood the systematic thinking behind it. Every Jeep among approximately 80 in inventory used identical components, regardless of which month or which plant produced it. Serial numbers indicated manufacture dates spanning nearly 2 years, and production at both Willys and Ford facilities separated by over 1,000 miles. Yet parts interchanged perfectly between vehicles without any fitting, adjustment, or modification. A mechanic working on a Willys MB, manufactured in March 1942, routinely installed a clutch assembly stamped with Ford markings, dated August 1943. The clutch fit precisely, operated correctly, required no special procedures or adjustments. This seemed impossible to German prisoners accustomed to German part numbering systems where component sources and production dates significantly affected interchangeability, requiring skilled workers to adapt parts during installation. Parts bins lining workshop walls contained items organized by function and marked with standardized numbers, identifying components unambiguously across manufacturers, production dates, and facilities. Part number 806591, designated water pump assembly. Every water pump bearing that number, regardless of who manufactured it, when or where, fit any Jeep in inventory identically. This wasn't approximation or close enough tolerance. This was precise interchangeability that American industry had achieved through manufacturing discipline, that German industry, despite its reputation for precision engineering, had not matched across multiple suppliers and production facilities. The bins contained dozens of common wear items, maintained in systematic inventory, controlled through written records updated daily. Oil filters, fuel filters, spark plugs, fan belts, hoses, gaskets, brake shoes, light bulbs, fuses. When a Jeep required service, the mechanic consulted Technical Manual 9 to 803 for proper part numbers, retrieved parts from appropriate bins, performed replacement following documented procedures, and returned the vehicle to operational status. The process reflected manufacturing philosophy, prioritizing reproducibility over individual craftsmanship, enabling semi-skilled workers to perform maintenance effectively through systematic organization, rather than requiring years of experience and training. Tool control boards provided specialized equipment, organized systematically rather than stored haphazardly. Socket sets arranged by size, open-end wrenches sorted by dimension, screwdrivers grouped by type, pliers categorized by function. Every tool had designated location marked on pegboard backing. American NCOs inspected tool accountability daily, ensuring nothing disappeared or migrated between workstations. German prisoners accustomed to more informal tool management, where mechanics kept personal collections, found this systematic organization almost obsessive initially. But efficiency became apparent quickly through daily work. No time wasted searching for correct tools. No disputes about tool availability or ownership. Every mechanic knew exactly where to find needed equipment and where to return it after use. The system enabled even relatively new workers to function effectively because tools and parts were organized for rapid location, rather than requiring experienced mechanics to know through long practice where everything was kept and which alternative tools might substitute when preferred options were unavailable. Preventive maintenance schedules dictated service intervals based on accumulated hours and mileage rather than condition inspection or mechanic judgment. Every vehicle received specified service at 1,000-mile intervals, regardless of apparent condition. Oil changes, lubrication service, using standardized grease gun at 23 fittings, specified in technical manual diagrams, fluid level checks, tire rotation following documented patterns, brake inspection using defined criteria, belt tension verification using gauge measurements. The complete service required approximately 2 hours per vehicle, following checklist procedures documented in technical manuals that eliminated ambiguity about what should be done. This scheduled approach seemed wasteful to German mechanics trained to service equipment based on evident need, rather than arbitrary numerical intervals. A vehicle running perfectly might receive complete oil change, simply because it accumulated specified mileage. German practice would defer service until oil showed visible degradation or engine exhibited symptoms suggesting service requirement. Why waste good oil that could serve thousands more kilometers? Why invest labor in maintenance that might not be necessary? But the American system produced measurable advantages that prisoners observed over months of sustained exposure. Scheduled maintenance caught developing problems before failures occurred during operations, when repairs would be time-consuming and vehicle unavailability would affect missions. Regular fluid changes prevented accelerated wear that would shorten component life. Periodic inspections identified worn components early, when replacement remained routine service rather than emergency repair, requiring expedited parts delivery and rushed work. Statistical analysis of maintenance records allowed prediction of parts requirements, ensuring adequate inventory without excessive stocks consuming warehouse space and capital. Hans Kruger, a former Unteroffizier mechanic from 21st Panzer Division captured during the retreat from El Alamein, worked motor pool details from September 1944 through April 1945. His English improved through daily interaction with American supervisors, who communicated work assignments, provided technical guidance, and answered questions about procedures that seemed illogical initially. Kruger kept private notes documenting observations about American maintenance practices, writing in careful German script in a notebook he maintained throughout his captivity. These notes, preserved after his return to Germany, following repatriation in 1946, provide detailed account of prisoner perspective on American industrial methods observed from inside the system. Kruger noted that motor pool operations treated maintenance as systematic process, measurable through metrics, rather than craft requiring years of apprenticeship under master mechanics. Records tracked repair times, parts consumption, failure rates, labor hours, costs. Supervisors analyzed these records regularly, seeking patterns, indicating problems requiring attention or opportunities for improvement. If specific components failed more frequently than expected specifications predicted, investigation determined whether faulty parts, improper installation, operator error, or design problems caused the pattern. Solutions addressed root causes rather than merely treating symptoms repeatedly. This data-driven approach to problem-solving, foreign to German craft-oriented maintenance culture, impressed technically minded prisoners who recognized its logical foundation despite initial unfamiliarity. Kruger wrote in his notes that the Americans treat vehicle maintenance like factory production, seeking to make the process itself efficient and reliable, rather than relying entirely on mechanic skill and experience. He observed that relatively inexperienced American soldiers performed maintenance effectively because the system supported them through documentation, standardization, and organization, rather than requiring extensive training and years of experience building expertise. The systematic approach extended beyond individual tasks to overall facility operation. Work schedules organized efficiently. Parts ordering followed established procedures. Record keeping maintained consistently. Quality control checked work before vehicles returned to service. Everything reflected thinking about maintenance as system that could be designed, measured, and improved, rather than collection of individual craftsmen working independently based on personal knowledge and judgment. U.S. Military Intelligence Service conducted systematic interviews with German POW mechanics during 1944 and 1945, seeking insights about German equipment and logistics, while also assessing prisoner attitudes and knowledge. Interview summaries compiled from Camp Hearn. Interrogations included noteworthy quotes from prisoners describing American motor pool organization with professional respect tinged with surprise. One summary reports prisoner stating that he observed organization unseen in Germany when characterizing American maintenance operations. Another quotes prisoner estimating that 5 years of peacetime industry would be needed to reach this efficiency, based on his assessment of current German industrial methods that would require fundamental reorganization to match American systematic approaches. These assessments proved remarkably prescient. though the prisoners making them could not know their observations would prove relevant to Germany's future. The connection between wartime exposure and post-war industrial development remains difficult to document precisely through individual accounts. No former prisoner claims to have personally revolutionized German manufacturing methods based solely on observations made while working Camp Hearn motor pool. Attribution is always complex, with multiple influences shaping outcomes. But aggregate patterns suggest influence extending beyond mere coincidence when hundreds of technically trained German prisoners returned home after sustained exposure to American industrial methods fundamentally different from pre-war German practices. The lessons German prisoners absorbed in American captivity would not prove immediately relevant. Germany's immediate post-war situation involved survival, not industrial planning. But as Reconstruction began and West Germany rebuilt its industrial base, concepts about standardization, parts interchangeability, systematic organization, and process discipline appeared in German manufacturing with emphasis markedly different from pre-war practices. The transformation involved multiple factors, including American Marshall Plan assistance, direct technology transfer, and explicit efforts to adopt American methods. But the foundation may have been laid partly through wartime exposure, when German technical personnel observed American systems from inside and recognized that different approaches to manufacturing and maintenance could deliver superior results. As the war entered its final year, the operational implications of these industrial disparities manifested with increasing clarity across every theater and every campaign. When Allied forces landed in Normandy during June 1944, logistics personnel immediately began compiling movement tables, allocating vehicles to units landing across the beaches. The process had begun months earlier during planning phases, but continued daily as formations expanded the beachhead and pushed inland against German resistance. Statistics revealed how material abundance translated to operational capability that German commanders, despite tactical skill, could not match. Between June 6th and September 30th, 1944, approximately 51,000 Jeeps landed in France, supporting Allied operations. These vehicles provided dedicated transport for functions that German units accomplished through shared vehicles, foot movement, or simply went without. Infantry regimental commanders maintained communication with forward battalions using Jeeps fitted with radio equipment, allowing real-time coordination. Engineers conducted bridge reconnaissance driving Jeeps to survey sites rapidly rather than walking for hours. Medical detachments evacuated wounded, using Jeeps fitted with litter racks carrying 4 casualties compared to hand-carried stretchers requiring 4 men per casualty. Communications personnel laid field telephone wire from Jeeps' unreeling cable while driving, rather than manually carrying heavy spools. Artillery forward observers directed fire missions from Jeeps, positioned with clear view of target areas, allowing rapid displacement when counter-battery fire threatened. American Infantry Regiment Organization tables authorized approximately 25 Jeeps per regiment, plus additional vehicles at battalion and company level for specific functions including reconnaissance, liaison, and command. An American Infantry Division, with 3 regiments, plus supporting units, possessed roughly 200 to 250 Jeeps, depending on specific organizational structure and attached units. German infantry divisions in Normandy possessed perhaps 20 to 30 light vehicles total, primarily Kübelwagens, supplemented by requisitioned French civilian vehicles and occasional captured equipment, pressed into German service out of desperation. The 5-to-1 vehicle density differential translated directly to mobility advantage, affecting every operational function continuously rather than episodically. American commanders moved between units, rapidly maintaining personal awareness of tactical situations that changed hourly during fluid combat. German commanders relied more heavily on radio communications when functioning, or motorcycle couriers when radio was unavailable or compromised, accepting delays of hours for information, and orders that American officers transmitted in minutes through direct contact. American units shifted reserves laterally along the front, responding to threats or exploiting opportunities within hours. German movements proceeded more slowly, constrained by limited transport and fuel availability that required careful rationing and allocation decisions. German infantry divisions in France during summer 1944 faced mobility constraints progressively worsening, as strategic bombing and ground combat attrited inadequate vehicle inventories faster than German industry replaced losses. By late 1944, German formations relied approximately 60 to 65% on horses for moving artillery and supplies, despite nominal mechanization of elite formations that existed mainly on organizational charts rather than in actual practice. Artillery batteries used horse teams numbering 6 to 8 animals per gun to tow pieces into firing positions, a method essentially unchanged since Napoleonic warfare. Supply columns employed horse-drawn wagons, moving materiel from railheads to forward areas at walking pace. Medical units evacuated wounded in horse-drawn ambulances, lacking any suspension, subjecting injured men to painful jolting over rough roads that worsened injuries and increased mortality from shock and bleeding. This reliance on horses represented not nostalgic preference for traditional methods or cultural attachment to animal power, but simple inability to produce or maintain sufficient motor vehicles under conditions of strategic material shortage, industrial bombing that destroyed factories faster than they could be rebuilt, and Allied air supremacy that destroyed vehicles in transit and at front faster than depleted factories could build replacements. Horse requirements for military operations consumed fodder tonnage that could alternatively transport ammunition or fuel if vehicles were available. Horses required veterinary care, fodder storage, and stabling in winter, protecting them from elements. Horses moved at walking pace of perhaps 4 kilometers hourly, requiring 12 hours to cover distance truck convoys, managed in 2 hours, fundamentally limiting operational tempo and tactical flexibility. German intelligence officers monitoring Allied operations noted patterns that defied comfortable assumptions about resource limitations constraining enemy actions. Luftwaffe reconnaissance photographs of Allied rear areas when aircraft managed to penetrate Allied air defenses showed supply dumps, vehicle parks, and fuel storage facilities covering square kilometers organized with systematic precision. Reports described Allied vehicle density per kilometer of front exceeding German estimates by factors of 2 or 3 based on traffic volume analysis, visual sightings from observation posts, and interrogation of Allied prisoners. Most troubling to German strategic planning, intelligence assessment gradually shifted from estimating enemy units and their composition toward estimating enemy vehicle density as critical metric for predicting operational capability. This subtle shift reflected recognition that material abundance rather than unit count or tactical proficiency determined Allied potential to sustain operations, absorb losses, and maintain pressure continuously rather than episodically. A German intelligence report analyzing Allied buildup in France during July 1944 noted clinically that the enemy possesses transport capacity sufficient to shift entire Army Corps laterally within 24 hours, a capability we cannot match with our current resources regardless of tactical skill or unit quality. Another report from September 1944 observed with resignation that Allied vehicle replacement rates exceed our loss rates, meaning their effective strength grows despite combat attrition, while ours diminishes progressively regardless of tactical outcomes in individual engagements. The recognition that Germany was losing the industrial war fundamentally, even when winning tactical battles locally, spread through intelligence services and eventually reached operational commanders, despite efforts to maintain to the past. Optimistic assessments for political reasons. By April 1945, as Allied forces closed on Berlin from east and west, the final accounting of war production documented the magnitude of the disparity that had shaped the conflict's outcome as decisively as any battle or campaign. German armaments ministry personnel compiled final statistical reports as the regime collapsed around them. The numbers told story of industrial inadequacy, masked temporarily by tactical excellence and fighting skill, ultimately overwhelmed by Allied material abundance deployed systematically. Germany's total motor vehicle production across all categories reached approximately 345,000 units during 6 years from 1939 through 1945. This comprehensive figure included trucks of all sizes, from light cargo vehicles to heavy haulers, military cars and light vehicles, including the Kübelwagen, half-tracks for artillery and personnel transport, motorcycles and motorcycle combinations for reconnaissance and communications, and specialized vehicles for various military purposes. Every motor vehicle built for military use in Germany and occupied territories during the war years fit within this total, representing maximum achievable output under total war mobilization. American production during the same period exceeded 2.4 million trucks alone, spanning categories from quarter-ton Jeeps to 5-ton cargo haulers. This figure counted only trucks, separate from approximately 640,000 Jeeps tallied independently as tactical vehicles rather than transport trucks. Total American military motor vehicle production exceeded 3 million units built under War Department contracts, specifically for military applications. This excluded civilian vehicles built for domestic market or Allied civilian use through Lend-Lease, counting only military vehicles. The Soviet Union, despite massive territorial losses during 1941 and 1942, costing over 60% of pre-war industrial capacity, successfully evacuated and rebuilt industrial facilities beyond German reach in the Urals and Siberia. Soviet truck production reached approximately 200,000 units during the war, supplemented by 427,000 American trucks delivered through Lend-Lease. The Soviet truck fleet, combining domestic production and Allied assistance, totaled roughly 630,000 vehicles, nearly double Germany's total motor vehicle production of all types. Britain contributed roughly 480,000 military motor vehicles through domestic production, despite facing German bombing and severe resource constraints. Canada produced approximately 815,000 military motor vehicles as part of Commonwealth war effort. Remarkable output from nation with roughly 11 million population. Combined Allied motor vehicle production exceeded 4.5 million units versus German output of 345,000. Production ratio of 13:1 told the story more clearly than any tactical analysis or operational assessment. Germany never possessed realistic possibility of victory once the conflict became prolonged industrial contest, rather than brief campaign decided by operational surprise and tactical excellence alone. General George C. Marshall's post-war assessment, widely quoted in official Army histories, associated Allied victory with 3 items that symbolized industrial capacity applied to military requirements. Marshall identified the Jeep, the Dakota, and the landing craft as representing the foundation of Allied success. The Jeep symbolized tactical mobility and logistics flexibility. The Dakota represented strategic airlift capability. The landing craft signified amphibious power projection. All 3 categories reflected American industrial capacity applied systematically to military problems, producing capability at scale that tactical skill alone could not match or overcome. By 1945, the United States possessed capacity to replace in 1 week what Germany lost in 1 month of frontline vehicle attrition. This replacement capacity derived from production rates sustained through 4 years of total mobilization. American factories built Jeeps faster than combat, consumed them accumulating surplus inventory throughout the war. German factories built Kübelwagens more slowly than operations required, creating persistent shortages despite maximum industrial effort. The cumulative effect over years of sustained fighting created vehicle density differentials that translated directly to operational capability differences visible in every theater and every campaign, from North Africa through Sicily and Italy and France into Germany itself. The lesson transcended specific vehicles or particular campaigns. Industrial capacity determines outcomes in prolonged conflicts between modern nations when combatants possess comparable tactical capabilities and fighting quality. Courage matters profoundly. Tactical skill shapes battles decisively. Training and leadership influence combat effectiveness fundamentally. But when adversaries both field competent forces employing similar tactical methods, the side with superior industrial capacity wins through sustained material advantage that tactical excellence cannot overcome indefinitely. As the dust settled and veterans returned home to rebuild shattered nations, the lessons absorbed during wartime found unexpected applications. The connection between wartime observation and post-war industrial development appeared most clearly in Germany, where military defeat created opportunity for complete economic reorganization. Wolfsburg, West Germany. By 1950, a post-war assembly line at the Volkswagen plant produced Type 1 Beetles for civilian market. The production methods showed clear evolution from wartime practices. Gauges systematically checked parts interchange, ensuring components met specifications consistently. Takt time boards posted at workstations displayed target production rates, focusing workers on rhythm and flow. Vendor qualification systems ensured supplier components met specifications before acceptance, eliminating downstream quality problems. Standardized part coding facilitated inventory management, enabling systematic control rather than ad hoc improvisation. These practices reflected concepts German engineers and foremen had absorbed through wartime exposure to American methods, whether through combat intelligence, analysis of captured equipment and documents, or through prisoner of war experience working in American facilities. The connection remained difficult to document precisely through individual accounts. No engineer claimed sole credit for introducing American methods. Attribution was always complex, with multiple influences shaping outcomes, but aggregate patterns suggested influence beyond mere coincidence. West German manufacturing, during the 1950s, economic miracle, demonstrated emphasis on standardization, parts interchangeability, and process discipline that differed markedly from pre-war German industrial practices, emphasizing craft traditions and artisan manufacturing methods. Volkswagen exports exceeded 100,000 units annually by mid-1950s, using production methods, emphasizing reproducibility and volume rather than individual artisanal quality and customization. The transformation involved multiple factors, including American Marshall Plan assistance, providing capital, direct technology transfer through industrial cooperation programs, and explicit efforts to study and adopt American manufacturing methods. But the foundation may have been laid partly through wartime exposure, when German technical personnel observed American systems from inside, whether as intelligence analysts studying captured equipment or as prisoners working American maintenance facilities, and recognized that fundamentally different approaches to manufacturing, standardization, and organization could deliver superior results, measured in productivity, quality consistency, and cost efficiency. The Jeep became unwitting teacher, whose curriculum covered not just vehicle design, but systematic industrial organization, standardization, enabling mass production, and process discipline that would prove valuable during Reconstruction. The human dimension of this story emerged decades later, when veterans gathered to remember experiences that shaped their generation and their nations. September 12, 1998, Münster, Germany. An Afrika Korps Veterans Reunion brought together approximately 350 men who served in North Africa between 1941 and 1943. Most were now aged in their 70s and 80s, gathering annually while they still could to maintain connections forged during war and honor comrades who had not survived. The reunion included memorial service honoring fallen comrades, social gatherings allowing old soldiers to reconnect, and historical presentations documenting unit histories and combat experiences for younger generations. Among the attendees, a former Wehrmacht mechanic who had served with Panzer Regiment 5 gave brief remarks during the memorial service. His comments, recorded by German historical researchers documenting veteran oral histories, were later referenced in reunion proceedings published by the Veterans Association and in military history journals studying the North African South. Campaign. The mechanic's observations, delivered simply without dramatic embellishment, included statement that resonated precisely because of its understated honesty. "We never had vehicles like this," he said when describing American equipment encountered during the campaign. He elaborated briefly, recalling examination of captured Jeeps in workshop settings during 1942 and 1943. He mentioned robust construction that surprised German mechanics, expecting flimsy mass production. He noted four-wheel drive capability German light vehicles lacked entirely. He remembered standardization, allowing parts interchangeability between manufacturers that German logistics never achieved. Most memorably, he recalled simply the numbers, noting that we saw more abandoned Jeeps in single battles than we received Kübelwagens in entire months. This told us something fundamental about American industry that we had not fully understood despite intelligence reports and propaganda dismissals. The statement reflected not defeat or bitterness, but professional acknowledgement of capability differences observed firsthand under combat conditions. German mechanics recognized engineering quality and industrial capacity when they examined evidence directly, even when that recognition confirmed uncomfortable truths about relative industrial capacity and material resources. The mechanic concluded his brief remarks noting that we fought well with what we had, but we were competing in different categories. We had technical quality, they had industrial quantity. In prolonged war, quantity decided outcomes, regardless of quality advantages. Other veterans shared similar recollections. A former signals officer described using captured Jeep for several weeks after his unit's Kübelwagen suffered mechanical failure that could not be repaired due to parts unavailability. He noted that the Jeep performed reliably throughout the period despite receiving minimal maintenance beyond fuel and oil, contrasting with German vehicles requiring constant attention to maintain operational status. A former Panzer commander mentioned seeing Allied motor pools during the retreat from El Alamein, describing vehicles lined up in organized rows as far as visibility allowed, suggesting reserves and depth we simply did not possess despite tactical victories. The conversation shifted between nostalgic reminiscence about youthful experiences and sober assessment of how material disadvantages shaped combat outcomes, despite German tactical skill and fighting quality. Several veterans expressed professional respect for Allied logistics organization, acknowledging that tactical victories in individual engagements ultimately proved meaningless against enemies whose industrial capacity enabled sustained operations. The Wehrmacht could not match given resource constraints. We won battles, one former artillery officer observed, but we were losing the industrial war from the beginning. Eventually, the industrial war determined everything, regardless of battlefield outcomes. The technical specifications that drove these recognitions remained documented in comparative analyses compiled during and after the war. The Kübelwagen Type 82 used 985 cubic centimeter air-cooled flat-4 engine, producing 23.5 to 25 horsepower. Curb weight approximated 1,500 pounds. The vehicle provided economical operation, low maintenance requirements from air cooling, eliminating coolant system complexity, and adequate performance on firm terrain. But two-wheel drive configuration limited capability in soft or steep conditions that reconnaissance units commonly encountered. The Willys MB used 2,199 cubic centimeter water-cooled inline-4 engine, producing approximately 60 horsepower, triple the German output. Combat weight reached 2,450 pounds, substantially heavier but compensated by greater power. The vehicle provided four-wheel drive capability, low-range gearing for difficult terrain, robust construction accepting battle damage and hard use, and standardized components enabling rapid field repair. Power-to-weight ratio favored the Jeep. Traction advantage proved decisive in operational conditions. Production advantage eliminated any possibility of German numerical competition. By 1945, the arithmetic closed the argument definitively. The United States produced approximately 640,000 Jeeps during war years. Germany produced approximately 50,400 Kelvin Kübelwagens total. 12-to-1 production ratio reflected different industrial capacities rather than different national will, engineering skill, or worker dedication. American factories operated with access to raw materials from secure hemispheric sources, protection from strategic bombing by ocean barriers, abundant electrical power from undamaged infrastructure, and large pools of adequately trained, skilled labor. German factories operated under progressive strategic bombing that destroyed facilities and disrupted production. Severe material shortages as supply lines contracted, frequent power disruptions from damaged electrical infrastructure, and forced replacement of skilled workers drafted into military service with poorly trained forced labor. The production differential was inevitable, given these contrasting conditions. What might surprise observers was not that America outproduced Germany, but the magnitude of advantage, once fully mobilized industrial capacity, engaged systematically. The 12-to-1 ratio in light vehicles reflected similar disparities across every category of military equipment, from tanks to aircraft to ships to ammunition, documenting that industrial capacity rather than tactical excellence or national will determined outcomes in prolonged modern warfare between industrial nations. The captured Jeep, examined in that desert workshop during November 1942, represented lesson written in steel and part numbers that German observers were uniquely positioned to read accurately. Wehrmacht mechanics discovered that American engineers had solved mobility problems through fundamentally different methods than German designers preferred. The four-wheel drive system added weight and complexity that German doctrine viewed as inefficient given resource constraints and traditional emphasis on mechanical simplicity. But that added complexity provided capability that German vehicles lacked, capability that mattered operationally in conditions where reconnaissance and support vehicles actually operated. The standardization between manufacturers that seemed to sacrifice precision engineering actually enabled superior logistics through parts interchangeability that German manufacturing methods never achieved, despite Germany's reputation for precision. The emphasis on accessibility for maintenance that appeared to waste design effort actually reduced repair times in field conditions, where rapid return to service mattered more than manufacturing economy or theoretical efficiency. Every design choice reflected different priorities, shaped by different resource positions and different assumptions about how prolonged industrial warfare would develop. The story of Wehrmacht mechanics examining captured Jeeps and later working American motor pools as prisoners reveals how material reality gradually overcame doctrinal assumptions and ideological certainty. German engineers had designed the Kübelwagen based on reasonable principles, emphasizing efficiency and economy, appropriate for a nation, expecting brief campaigns with limited resources. American engineers had designed the Jeep based on different principles, emphasizing capability and producibility, appropriate for nation, possessing abundant resources and expecting prolonged conflict, requiring sustained industrial output. Neither approach was inherently superior in abstract theoretical terms divorced from strategic context. But the strategic context that actually existed favored American approach decisively. Industrial warfare requires industrial solutions applied systematically at national scale. The nation that treats military production as industrial problem, subject to systematic engineering analysis and process optimization, gains cumulative advantages over nations treating production as craft, requiring traditional methods and artisan skills inherited from pre-industrial eras. The Jeep proved this lesson through simple existence in numbers that German production, constrained by resources, bombing, and organizational limitations, could never match regardless of effort or sacrifice. By war's end, the arithmetic had demonstrated its conclusion with finality that permitted no argument or alternative interpretation. America built 12 Jeeps for every Kübelwagen Germany produced. Allied forces maintained mobility advantage through vehicle abundance that German forces, despite tactical skill, could not match. The operational implications cascaded through every campaign, from North Africa through Sicily and Italy and Normandy and France into Germany itself. Strategic implications shaped the conflict's outcome fundamentally. The captured Jeep in that desert workshop was not simply a vehicle for German mechanics to examine and document. It was evidence of industrial capacity applied systematically to military requirements, and that capacity proved decisive in ways that courage and skill alone could never overcome. The numbers closed the argument. The lesson remained. If you value fact-based military history that reveals the hidden mechanisms of victory, subscribe to support content grounded in archival research and documented evidence rather than speculation and myth.